Dan Kokron is back with us this afternoon to talk about programming frameworks.
Good afternoon. Let's see, just to add to the confusion of all the information you've been trying to decipher the last couple of days. Hopefully the idea of a framework is to hide a lot of the complexity of the computer and enable you to write a parallel, efficient code without having to worry about all the MPI stuff or actually the underlying computer itself at all. So why use a framework? A framework hides the computer science, basically. The hardware type and configuration, operating system, OS stack. Presumably, the idea is that if you write a program with the framework, under the framework, that the hard part of actually getting the program to run on any machine available or in the future has already been done by the framework developers themselves. For the solitary scientist, you can implement an algorithm without worrying about the computer architecture, and it also facilitates collaboration with other scientists who also program to the same framework, so that for instance, an atmospheric GCM is composed of a lot of components like an LSM, the atmospheric dynamics, there's a chemistry component, there may be an ocean involved, and all these can be developed independently, and if they're written to the same framework, they can be combined together and then work together. And I'll just reiterate, the framework provides an abstraction of the underlying computer. What do they provide generally? Routines to parallelize an application. Specifically, the ones I'm familiar with are domain decomposition, but they all tend to ride on top of MPI so that you can do all of the same things that MPI will allow you to do. It's just, like I said, it hides a lot of the complexity. Routines to allow processes to communicate. In the MPI world, that would be sends and receives and all reduces, but they also hide the complexity of halo updates. If you have a decomposed atmosphere running on different processes, and you have, say, the US running on one process and Europe on another, there's a seam there, and you have to worry about exchange of information across that seam, and the halo update does that. And computation of global values is another added feature. Routines to manage model time, such as calendars, clocks, and alarms for scheduling events. And this is nice because if you don't want to write out the state of the code every time step, you can schedule an alarm to do every 10th time step or something like that. And this is used a lot in the GEOS5 model to schedule their history component. A user may want a particular diagnostic out once a day, and something else out every model time step, and this allows them to create different files, different collections they call them, and do that. It adds a lot of routines to allow runtime control of an application. In Fortran, this might be handled by a name list argument, but for this case, you don't want to change the model tuning parameter and have to recompile and then rerun. This will allow the outside world to interact with the executable, you to interact with the executable without recompiling. And I'll show, I have an example of that later on in the talk. Routines to allow separate components, like I said before, of an application to communicate. Ocean to atmosphere, LSM to atmosphere, and back and forth. Another nice thing a nice feature of a framework is uniform error handling and reporting. If there is a problem with a call in the program, it will handle it and hopefully print out a useful error message where and why the error occurred. A framework may provide an interface to third-party libraries like FFTs or PDE solvers, routines for parallel I/O, and some level of performance evaluation. Simply calipers, so where you can add a start call around a particular loop that you think might be taking a long time, and that would be the user code here. And then stop the timer, and then you can print out a time, print out the elapsed time. Some frameworks that are out there: the Goddard Earth Modeling System, GEMS. It's been around for quite a while. It's, I believe, still used in some codes at Goddard. The GFDL Flexible Modeling System, the GEOS 5 Dynamical Core is written in FMS. So this is actively being developed and supported. And the one I'll be talking about is the Earth System Modeling Framework, also known as ESMF. And here's a website to get you started on what that is. Any questions so far? I've gone through a whole lot. To show you the power of what a framework can do, what I did was write a 1D and 2D diffusion example like we went over a couple days ago. That one was in straight MPI, but this it's written in ESMF on top of MPI. I make calls to decompose the problem in 1 and 2D. I make calls to, it allows the ability, I have used the ability to read in parameter settings from the outside world using the configuration option. And written here is the, well, I don't have the entire, of course, SVN checkout. I have a SVN repository, a code repository on Pleiades that I've developed this under, and I'll give you guys access to that so that you can check it out and play with it. Code walkthrough. Can you guys see that? Is that decent? Okay, what I have here is just a directory with some codes in it. First the 1D code here and its corresponding resource file, which has in it just the number of points in the x direction. And of course it's the duplicate of yesterday's 1D problem. In this case, we can change the material parameters of the solid that we're interested in, and that's done with this parameter here. We can change the number of iterations from the outside world without worrying about recompiling. And here we have the output interval. I put some on, I created an alarm, and I put that alarm inside the iteration loop, and I test the alarm every 0.1 seconds. And if the alarm is going off, then I write some stuff out to disk, and then I keep going.
Is there a way you can make that a little larger? Your font size and your X term?
I may.
Store your resolution and can control by 768.
I'm not now. Does that do it?
Yeah, it's a little better.
Yeah, that is better.
Anybody know how I can get to the bottom of this window now?
Set the green. I'll sign on the top left.
Okay. Now let's walk through the code a little bit. Since we are using MPI under the covers, we need to include the MPI GUI, if you want to call it that. We're going to be using netcdf to do our output to disk, so I'm including netcdf magic there as well. This is these are declarations of various parameters, and I'm not sure what that stuff is on the outside. In this case, the framework is started with an ESMF initialize, which I don't see here for some reason. Here we set up we create a configuration, internal structure inside ESMF that handles the configuration options. We load that configuration at this point, and then we read in what's in what we think might be in there. And if there isn't a setting in the file, we can specify a default here for what we think will be reasonable to have. This call, the vmget, allows you to query ESMF and get various MPI related, like the pet name or the pet number. Well, we call it a rank in MPI, but in ESMF it's called a pet. So we get the rank, local pet, and number of pets. And here's an example of the error handling. For this case, we're computing a delta X for our computational domain and a corresponding delta T to go along with it, assuming that we are satisfying the stability condition, and that this does that. I'm creating a calendar to keep track of, so we can build an alarm on clock of that. And there are various different kinds of calendars. I'm using the Gregorian calendar here. Going to set a time interval for the alarm. For the integration of the heat equation. Initialize a start time. This is very arbitrary. Start time and a stop time. Create the clock. And here, we're going to set the interval for the alarm to be this output interval, which is also settable from the configuration file. Here we create the alarm. In this code, I'm creating some information that's going to be useful. Goes into the file. It's not used in the calculation, but it makes it helps make the file readable for the outside world if you have latitude and longitude dimensions in the netcdf file. And this is our domain decomposition. It's a 1D left and right with halos on the borders. And again, ESMF will handle all the communication between those processes. And the DE number here is akin to the rank. So rank 0, rank 1, rank 2, rank 4. I'm going to run this on 4 processes. In order to do a decomposition, we have to create a grid first. So we're going to do that. We're going to go from 1 to the number of points in the X direction that we specify either in the configuration option, and we're going to break that up into the number of pets. Here we create the grid. Now we're going to put an array and then a field on top of that grid. And here we specify how many halo widths that you want. Now in this case we're using a single value for the halo width. If a higher order approximation to the heat equation may require more information from farther away. And you can have 2, 3, or 4, or as many as you really want, but it depends on the algorithm used to solve the equation. I do know that in the FV they generally use information from 3 points away. You can specify where the field lays on the grid. For instance, you can be at the center of the box, or you can actually be you can specify that the value is actually on the face of one of the boxes. And they do that in the numerical community for reasons I'm still not familiar with. Maybe Bob can add to that. But it has some numerical advantage, at least in the weather community, to have the U and V values not co-located with, say, pressure. And this allows that to be taken care of. This stagger location allows that to be taken care of very, very easily. Now that we've created a field, we're going to get, during this field creation, it figures out who owns what. It figures out all this ASCII business up here. And now we can go and query, each process can go and query its own portion of the field and figure out what it owns. Since it's an initial value problem, we're going to set the initial. Each process goes and sets the initial value to 20, and then if it has a lower bound to the left, it's going to set it to 10. If it's on the other side, it's going to set it to 40. And since we need to keep two values of the solution in memory at any given time, we're going to create a second. We're going to basically create a copy of our initial state and make it called temp FRA. This call creates a structure within ESMF that tells every pet where it needs to communicate. And this is basically how the processes are going to communicate with its neighbors, the halo information. And then once this is done up front, you can reuse that same structure over and over and over again during the calculation. Now, in order to write stuff out to a netcdf file, you went over some of this yesterday. Steve went over some of this yesterday. You have to create the file, create dimensions, create the variable. Normally in the weather community, they have a variable and a dimension of the same name. And then here we're putting some attributes on that. In this case, we have just one horizontal dimension, space dimension, we have a time dimension, and then down here we have the actual variable, which we call field name. It's a double precision. It's 2D, lawn, and time. And then we have the return value from here is a variable ID that we'll use later on when we're actually writing to the file. For parallel netcdf, you have to specify these start values and the counts, and that's done here based on the bounds that were calculated within ESMF. And now we get to the actual calculation. And I claim this is all actually easier than writing MPI, but your mileage, you may have a different opinion. In this case, we are going to, instead of stopping when the solution reaches some level of precision, we're going to run for a certain number of time steps and then quit. So that's this loop here. The inner loop that does the actual update of the solution runs from my lower bound to my upper bound. And again, that is determined by ESMF. Here's the solution calculation where we have the new solution, the temp array, F array, takes on some value of the old solution, and I hope you remember that from the recursive relation I showed you a couple days ago. That's basically what this is, with the material parameters specified here with this alpha. Now that we have one update of the solution, we do a halo update. We advance our clock one time step. We check if the alarm is ringing. If it is, we go into this if statement. We get the current time. We convert it to a seconds that we're going to write out to the file. We write the current state of our pointer. All right. But we're only writing our portion of it, where we have the exclusive lower bound and upper bound here, and the code is actually cut off for some reason. And then once the variable is written to disk, written to the file, we write the actual time. Once we're done with writing our done writing our output to disk, we turn the alarm, the ringer, off, and we return to computing. And that goes for the number of iterations we specify. We close the file after we're done with the close, and we do some cleanup. Field halo releases the internal structure. We destroy the field that we created, destroy the grid and the disk grid, and then we finalize the whole framework just like MPI finalize, and then we're done. The one drawback I can think of related to ESMF is that if you don't happen to use all of the features, it can be quite cumbersome to write a simple program. However, if you make use of all the halo updates, and there's also, ESMF also has some very sophisticated regridding, so that if you have an ocean on one grid and an atmosphere on a different grid, you can do that exchange very easily, all in one, all with one package. You don't have to write that code yourself, and you don't have to debug that code yourself, which is probably the harder part.
Does that mean that ESMF has spawned a lot of new modeling efforts?
I wouldn't say new modeling. GEOS 5 is the one that I know of that is completely ESMF. And that's the one I'm most familiar with. So. Mm-hmm. The National Weather Service has some plans to move this way. I don't know how far along they are. But the ESMF website has a list of its sort of clients, the people who are using